So we've talked about solutions and behavior of solutions. So let's actually talk about measuring the amounts of material in solution. This is the idea of concentration. Go into the lab and grab myself 5.8 grams of sodium chloride. A nice little pile of sodium chloride. And I toss that pile of sodium chloride into a container and then fill it up with water, say 350 milliliters total. I now have this 5.8 grams dissolved in that 350 milliliters. The ratio of mass to volume is consistent. If there was more mass in there, we would call it a more concentrated solution. Well, mass is all fine and good, but as we've seen, mass isn't all that useful for us. Turns out that 58 grams of sodium chloride is pretty close to 0.100 moles of sodium chloride. And we can figure that out from the molecular weight of sodium chloride. Well, what we have now is 0.110 moles of sodium chloride in 350 milliliters. Or we could rewrite this 0.100 moles of sodium chloride. If we convert it to liters, 0.350 liters of solution. And this would give us moles per liter if we were to do our calculation. 0.285 moles per liter. Well, that means that if I were to pour out 100 mils of that solution, 0.1 liters, I would have 0.0285 moles. What we now have is a way to relate the number of moles of a compound to the volume of a solution via this concentration. Now, there are many different relationships for concentration. We've already introduced one of them, parts per million, which is milligrams per kilogram of solution. Milligrams of solute per kilogram of solution. So a 20 part per million solution would be equivalent to saying 20 milligrams of solute is equal to 1 kilogram of solution. And under dilute solutions, we can make the assumption that this is liters. So it allows us to relate these quantities very easily. Another common one is mass volume percentage. We could say that 3% sodium chloride solution, this would represent 3 grams of sodium chloride in 100 milliliters of solution. Mass volume percentage is another way of expressing large concentrations. Both of these, parts per million or parts per billion, are all very convenient, but they aren't very chemical. And so for chemical quantities, we introduce a new quantity, molarity, given the symbol capital M. And in my chicken scratch, I will underline the M to represent the M. So molarity is defined as moles of solute per liter of solution. That is the definition of molarity. So a 2.33 molar solution of sodium chloride means that 2.33 moles of sodium chloride are found in 1 liter of solution. So that's the definition. It's a concentration. It's a measure of how much. And so we standardize it to a liter. But we don't always have a liter. If we had 0.35 liters of solution, that was 2.333 molar sodium chloride, how much sodium chloride would be in that solution? Well, we can set that up, 0.35 liters, and then from our definition of what molarity is, moles per liter, we can convert this volume. 1 liter of that solution would be 2.33 moles of sodium chloride. And so we could use that volume to find the number of moles. It says that in that 0.35 there would be 0.815 moles of sodium chloride. What this means is that if we know the molarity and we know a volume, that is equivalent to telling us the number of moles. What that means is now we have a new way. So we have our mole of X to mole of Y inner conversion. And last week we were talking about using grams and the molecular weight to figure out how many moles we have. We also talked about atoms and Avogadro's number tell us how many moles we have. Well, today we've introduced a new one, molarity, along with the volume, gives us the number of moles. And then we can go back as well to grams and the molecular weight and atoms using Avogadro's number, or we could convert back into other molarities and other volumes using known quantities. So we're going to pick up there next week using molarity and finding molarities from information in a problem.